It's near the end. Okay, guys, here's the deal. Since it sounded like the project information has not been properly conveyed to everybody, I'm saying it into the camera right now. I hope this is getting recorded. A week or two ago, we went over just some project ideas, and what I'd like everyone to do is some either solar thermal or wind project. And it sounds like everyone's mainly into the solar thermal in some way or another. Now, if you're at a loss as for what to do for a project, one idea I had for you in particular, Ryan, if you'd like, if you're so inclined, this is just relatively easy. Well, I shouldn't say well. It's something that I think is important. And I'm also thinking that Adam Kopic, who's still out there in cyberspace somewhere, would be another good teammate for you to work on this project. And here it is. Tomorrow, you guys are going to go to Nikki Robinson's house as a class, as a group, with our faithful TA, Tim Chester, at 9 a.m. I'll be there if I can. Tim has the insulation meter with him so he can see how much sunlight is at least hitting our house at 9, and it's not going to be the greatest data because who knows, it could be really sunny or cloudy. It's just going to be one data point. But you've got the instrument there. He's also going to bring the Solar Pathfinder. The purpose of the Solar Pathfinder is to basically integrate and predict how much solar radiation you're going to get throughout the year. And so what it does, have you guys seen this technology at all? Solar Pathfinder? I'll just I'll scribble something out to basically give you the.
Doesn't it just track during the day?
It doesn't track. It does not track at all.
Is there an incident plane that it hits?
Keep guessing. No, I'll tell you. what it does. I'll draw two different views of it. One is a top view here, and if this is south. And let's just say you've got like a tree over here, and this is top view. We're looking down from an airplane view, straight above. And maybe you got a house over here. The profile of the Solar Pathfinder looks like yay. So from the side, it just looks like a hemisphere or a fraction of a sphere there. And so what ends up happening is light from everywhere comes in, hits this sphere, and is just projected down onto this circular surface. And the circular surface, actually, let me grab you rather than try to screw it up. Solar Pathfinder. Video software analysis tool. I need the sample sheet. Let's just try that. Look at images. Okay, this is what the thing looks like. So if you're looking at it from above, it's glass. You get a little bit of reflection, so you can kind of see your reflection in it. But looking in a little closer, the horizon is sort of projected or reflected down onto this surface. And so you don't, I mean, you get a full 360 degrees, but as you probably know, unless you're like at the Arctic Circle, the sun never comes from the north. It's always, roughly in the south, somewhere, depending on where you are. So it's obviously more than 180 degrees. I mean, you probably noticed, especially here in Montana, where the sun sets, it almost looks like it does a lap around you on December 20th. So that's why it's shaped like so. But what you end up with is a little line, and you trace this little line on your graph, and your graph has these lines on like this. I'm not doing it a whole lot of justice here, but I think you'll get the point. Let me, and I'll redraw my, so this is the line that you come up with. And if we go back to this guy, you go back to this guy, you can't see him all that great, But there's little numbers here. It's like a 1, 2, 3, 4, 5, 6, et cetera. That's how many hours of daylight you get. And so each one of these lines is an hour. And so at the end, after you take your horizon, and again, well, I should have drawn this a little bit better. This little chunk could sort of be the shadow of the tree right here. This little chunk could be the shadow of the building. And so the more shadows you have, the less real estate that you end up with. And so what ends up happening is this is all losses. And this side is all gains. And so if you had no obstructions whatsoever, you get full sunlight. And the other thing to note is that these little sheets themselves, well, you can see 37 to 43 degrees north latitude. That's right there in that top latitude specific. This is not valid for us because we're at 46, 47, so we've got to make sure you got the right sheet in there too. But what that'll do, it'll give you an estimate of how much solar thermal energy is going to hit your technology. Clear? Good? Okay. So that's that. Getting back to your project, what I would like to see happen on Nikki Robinson's installation is this. So here's her garage. Here is the device, solar thermal. I'm not going to write STD because that's something else. Solar thermal system, STS, solar thermal system. Sorry, yeah.
Is it ground mounted?
No, it's designed to be bolted onto the building like so. There's a nice frame.
Like not on top, not roof? But
No, just on the wall, side mounted. And it's got a,
So do you mount the Pathfinder at that same angle? Or?
no, no, in fact, that's a great question, Joe. The Pathfinder itself, so the question is whether you mount the Pathfinder at that angle. The beauty of the Pathfinder is that, so again, this is top view over here. This is side view right here. Is all of this light, so the short answer is no. It's always face up. That dome, the very top of that sphere points straight up. And what ends up happening, the light, when it hits this dome, then comes down for you and is projected onto the surface. That's kind of how the thing works. It hits that little curve and projects, a spherical universe onto a circular disc. Onto the circular disc. That's it. So you don't have, I don't say it's not important. You actually have to level it. It's critical that it is level, because if you start pointing it, then you're not truly looking at the horizon as it is.
So do you put it at that elevation?
Yeah, absolutely. Yeah, that's the critical part. You put it at the right elevation. Obviously, you get it up too high, you're going to be out of the shadow of that tree in that building. You get it too low, and you'll have more. So that would actually not be a bad little thing to do. So you might imagine tomorrow putting it down here, and you might come up with something like 4.4 hours average. And let's say you stick it up here, you might come up with a different number. And that might not be a bad little exercise to do tomorrow and say, okay, up here it's 4.8, and then we can just say the average is 4.6 hours. And it'll give you hours of sunlight. It's then up to you, the technologist, to turn that into watts. And you'll then need to decide, do I want to use the solar constant of 1,000 watts per square meter? Probably, based on the fact that we're at 45 degrees approximately latitude. I don't know if you guys remember all that stuff from 102, but if this is the Earth out here, sun's way out here, you got your atmosphere, top dead center, your solar constant something like 1386 watts per square meter. But then as you get over here, you're looking through more atmosphere, You guys remember all this stuff? Starts to drop off. Obviously, if you're over here, it's 0 watts per square meter on the backside, but somewhere in between is anywhere from this very maximum value you're going to get, 1386 versus 0. But the average, the accepted average is 1,000 watts per square meter. So yeah, good question. But you can take it at an elevation of, let's just say 3 feet. You can take it at an elevation of 8 feet. Get those two numbers, and then that's enough precision, for this thing. And then in fact today, what I want to do in the next half hour, as soon as we go through this little project deal, is show you how to calculate how much power to expect from one of these guys. Okay, so here's the deal. We're going to have cooler air coming in through the bottom of the system. We're going to have warmer air, pink, coming out the top of the system. And what am I talking about? Well, here's the gizmo. This is a little model that Tim Chester made for the actual system. It's sitting in my yard now. He's going to grab it in the morning, take it to Nikki's. But what we're looking at, so I'm just going to face this thing in the same way that it would face in use. So I'm behind it. The sun's coming in here. It hits these cans. They're painted black. In theory, something that's black, what's it going to do with the radiation? You got 3 choices. It's going to absorb it all, right? So it comes in, radiation gets turned directly into thermal energy because all those photons are now shaking around inside the, they've taken all the electrons, orbitals, popped them up into greater shells. They're probably not smacking the nucleus. They've energized each of the atoms. They're all vibrating more quickly. The heat that's then in the can, some of it, the majority of it, gets transferred through conduction into the air that's inside the can. And now what we've got with the system is some just natural convection. We did Bernoulli's equation last time to show you that density, remember there was density in Bernoulli's equation, something that's less dense, it's hotter, goes up the top. As it turns out, this thing gets so hot so fast that just natural convection is not enough to move that heat through. So there's a fan that actually forces air, pressurizes here in the bottom manifold, forces air up through into the top manifold where the hot air then comes and heads into the house right here. Okay. Now, there's a couple problems with the system as it is right now. It is no control system.
So there's no temp.
There's no thermostat on it. So what I'd like you and Copic to do, if you could, I'm just throwing it out there, is a doable project that would really save the day for this thing, would be to put a thermostat right here that Nikki Robinson can mess around with. And what the thermostat should tell you that if T greater than T hot, basically I don't want it any hotter than 90 degrees in my garage, then fan equals off. Pretty simple. And so you could use so this thermostat could be an old junky Mercury thermostat. I think I got one in my office. If not, I'm sure there's a big box of them over at Home Resource. If not, probably buy something online, and we have money to buy it. So I think that's about all it needs.
Well,
And otherwise, oh wait, no, I'm taking it back. That's not all it needs. It's not all it needs. It's not all it needs.
It seems like you want some louvers to close the holes up.
Oh, absolutely, yeah. That'd be great too.
it all depends if you think the cans will get hot enough to, if that's the type of insulation, doesn't that foam insulation get too hot too?
It has no more foam insulation. We took all the foam insulation out of it.
But you replaced it with other insulation.
No, it has nothing in it at all. It's just bare naked system. And, you know, it's better than nothing, you know. it's-
So if it's a non-heated garage is what we're going with, right?
Yep.
Okay.
Yeah.
So, in my mind, if you have this on all the time, it works as both heating and cooling for your summer and winter.
It could. Now, that's that's kind of a next level
Even
of
if you turn it
complexity.
off, it's gonna have heat. That heat has to go somewhere.
Yeah, so what we did for that heat that has to go somewhere is drilled some holes in the top and put little caps on them. So the default mode in the summer, our control system in the summer was just take the caps off and just let the heat go back out into the atmosphere where it was going to go anyway. But,
Put a cover on it so rain won't fall in.
yeah,
Oh, man, afterthoughts.
no, how do we deal with that? I don't remember rain being a problem. Maybe we put them in the back. I can't remember. Maybe they're just sitting right here. I think they are. They're just in the back. We didn't have any rain problems with it. The other issue that we'd like to have happen is it can't just be if the temperature. It can't just be if the temperature in here, because you're going to need to know what the temperature is. Let's see, temperature garage, and you got the temperature of the system. And so what we're looking at is if the temperature of the and temperature TA, so TH equals high set point. TS equals temp system. And so in this case, we're going to need some kind of, well, either, like I said, a mercury thermostat that's got its thermocouple sitting out here with its other one inside the garage, or some kind of electronic that can measure this temperature difference. So if the temperature in the system is greater than your set point, you don't blow any air. Now let's think about the next one. If T system is greater than T cold, and there's an ampersand, sun equals on, then, and I think that might be redundant. I'd be surprised if the temperature in the system was hotter than the temperature in the garage, simply because your house in general at night is warmer than the air. Anyway, think that one through a little bit. Then, fan equals on. Does that make sense as a control system? It's fairly simple.
Yeah, nothing
It can only be on if the sun's up.
Yep.
is, like a normal thermostat.
And we've got a PV panel that is only going to give you juice when the sun's up, so
Yeah.
that's already on there.
Although you would want a system, because as soon as the sun comes up, the PV is gonna capture more energy than the solar thermal system itself.
Probably.
Right off the bat.
Yeah, probably. Yeah,
So you might want some kind of control system for that to not power the fan until a
Right,
certain time.
right,
Like for
right.
an hour, the sun's up.
yeah, and that's why I'm saying, and, this is the ampersand right here. The sun's on, and the system is warmer than your set
Oh,
point, because you don't want to start blowing cold air in. Okay, so temperature hot is high set point, TS is temperature system, we're running out of space here, TG equals temp in garage, and I'll write it up here, TC equals low set point. So I think we got all the logic statements there on the thing.
Won't the temperature of the system be greater than the TC most of the time?
Will the temperature in the system be greater than TC most of the time? Probably most of the time, but not necessarily at night, because that thing's going to be hanging out in the freezing cold, and your garage is relatively warm, and you don't want to be blowing cold air into the garage. That's what you want to avoid. It's like making. But on the other hand, I think we were going with that. You could use it to that purpose in the summer, at night, to blow cold air into the garage at night. Absolutely. But let's just leave that for another project.
Yeah, let's leave
Okay.
that for another day.
All right. So hopefully, Adam, you heard that, and Ryan, maybe you guys can partner on it. Adam I think he can shop for controls remotely and help you design it remotely, and you can be the boots on the ground. Save the day for Nikki. Come on. She'd love it.
Just slap her on there.
Okay. All right, so hopefully that answers that question. So that's a wrap on projects. We went over projects with everybody else, I think, last time. What I'd like to see by next week, let's even say like early next week before class, something I can just go over and kind of give it the thumbs up or thumbs down, is just 1 page project description with, I'd like to see timeline. Pretty important now since we're getting close to the end of the semester. And I know, Dustin, you kind of had a challenging project. Did I pair you up with somebody though?
Yeah, he told me to get one of Ernie. I messaged him.
Okay,
You could talk to him like Rex with his class. He has math right there.
that's good to know. Ernie Orr, get in touch with Dustin ASAP. We're counting on you for a cool project. So timeline, supplies needed. So we can just buy those now. Kelly Wasson has been great about buying stuff for us for other projects. I just got the batteries in for the Shell Eco Marathon car, by the way. And then I'd like to see a plan for collecting data. So I've got a bunch of these little USB temperature sensors. You can use those.
That one.
Got one, nice. We've got a thermal imaging camera. That'd be nice too. Shoot your system. I'd also like to see a little theory. Well, as in an appropriate amount of theory. I don't want you to go nutty, crazy. Just give. And the theory is just there to predict how the system's going to work.
This is all in our one-page
It's in
paper.
your one-page paper.
Is this double spaced?
No, man, come on. I mean, a timeline.
Sorry.
Do not get started with me. I've written so many bleeping proposals.
Sorry.
It's okay. But just like a timeline is four lines. This is what's going to happen for the rest of October. Here's November. Here's December.
Oh, you mean-
Supplies needed is going to be a list of 4 or 5 things that needs to get bought. There's another five lines. Plan for collecting data. That's 3 or 4 sentences, and a little theory. That's 3. I mean, it's 4 paragraphs really. It's nothing. It'll fit. I've seen you guys on your summaries. I know you can do it. 1 page by next week. And so this is by we teach on Wednesdays. So let's just say by Monday. And what are we looking at? Monday, that's the 3rd, the 10th, week 12.
You want us to email you
You
that,
can
or
email it, yeah, I don't, unless,
or just bring it in
unless I email you and tell you there's a place to upload it in the shell, which I know there was before, I just have to revive it, email it to me, yeah. By Monday, November 10th.
Can we just slap it in the project discussion?
Yeah, you can put it there. Just let me know where it is. Don't hide it up there and tell me I have to go looking for it. Just,
Well,
you
no,
know.
email and then slap it. in.
That sounds
Other
good.
people
That sounds great, yeah. That sounds great. Okay, we good on projects?
Yeah, let's do some stuff.
Good, let's do some stuff.
That'd be great.
I saw,